Hello, everybody. So I think we can start today. I will start a sharing. So let's start. So last time we talked about uh, transferring models for part-of-speech tagging across languages, and uh, the main device for that was a parallel corpus with word alignments. There will be also, or there have been actually techniques that use the same approach for parsing and dependency structures, and I will be talking about them in the subsequent lectures later. But today we will look at parsing and porting parsing models to new languages using something different, using essentially the part-of-speech tags. So the idea is that uh, part-of-speech tags, especially if they encode more than just the main coarse-grained part of speech, but some other categories, often tell you a lot about sorry, how the word behaves in the syntactic structure. And parsers can sometimes use it even without knowing what the word is. So here is the first example of that. Uh, there is a Danish and a Swedish sentence. Danish is the upper one and Swedish is the lower one. And they are parallel. They are taken from the JRC Aki corpus, from the various materials of the European Union. So they were the documents were automatically aligned sentence by sentence, and then we could run word alignment as well, but that's not part of the corpus. So these sentences essentially are taken from both of them probably were translations of something else. It is possible that the source language was Danish or Swedish, but I would rather think that source language was one of the other EU languages. And you don't have to speak Danish or Swedish to be able to see that there are some striking similarity between the sentences. And if you see the word alignment, or if you use the translation service, then you will see that even better. So there's this öffentlich göras, whatever the pronunciation should be, and similarly öffentlich göras in Swedish, and och is the conjunction, and these two words are also very similar, and po is a preposition. So even though only the red highlighted words are really identical in both the languages, we as humans can see that there is much more in common, which it should be actually, because Danish and Swedish are quite closely related. And the middle lines are the corresponding sequences of part-of-speech tags. In this case, the part-of-speech tag set is the one originally designed for English. It's the Penn-Treebank tag set, so it's not natively designed for either of the two languages, but the part-of-speech tags were converted to one common tag set so that we can see the possible differences or similarities, and also because in the actual experiments that I will speak about in a few minutes, in those experiments I needed to use the Penn-Treebank tag set because of the tools that I had. So if you look at the part-of-speech sequences, you see that again it's very close to each other. Now the highlighted ones are not the ones that are identical, but the ones that differ. So there's only this difference. There is a preposition here in listen is extra because in there is one e here, another e there, while in Swedish there is only one of them. And so maybe it's actually the second one, the belaget. And there is a modal verb down here. That's the skull in Swedish, while in Danish it's done somehow differently. I don't speak Danish, so I can't tell you what exactly the details are. But otherwise, it is obvious that there is a lot in common that the parser could possibly look at. And now if we look at the syntactic structure, this time it's not the dependency structure, it's constituency based, so it's just bracketing. I will tell you later why. It's basically just because of the tools that were available when I did this for the first time. But it doesn't matter, it's still syntax. So even for the constituency based trees, it should hold that there will be something in common between the two languages. And indeed there is. There is this constituent VB, CC, VB, which occurs in both the languages. Its parent constituent is slightly different because of the modal verb in Swedish. But then again, there's this in DT and N, which is again the same structure in both languages. The beginning is also more or less the same, and only where there is this extra constituent in Danish, it calls for a different treatment. So as you can see, the parsers, if you have a parser that will be trained on one of the languages, and if the parser ignores the actual word forms, the strings that are different in the two languages, then it still should be able, just based on the text, to do something, to create some output that will not be completely random, but will somehow reflect the structure of the sentence. So that was the initial motivation. It was published by myself and Philip Resnick in 2008, but the work is even older. We did it in 2006 in Maryland. And so I will show you the experiments that we did and the results that we had that time. Later, I will show you also the follow-up research done by other people. So 2006 was the year when there was, maybe for the first time, a significant collection of tree banks. Those were the dependency tree banks from the Connell shared task for multiple languages. So I think it was something like 13 languages available. So it was substantial, because before that everyone was working either on English or possibly on one particular other language with their own annotation style and file format. So now there were 13 languages with the common file format but not common annotation style. We will talk about it later. So one of them was Danish dependency tree bank, the other was Talbanken for Swedish, and these were the two most closely related languages in terms of genetic relationship and also their properties in the set that was available there. So these were, at least seemed to be, the perfect candidates for any experiment of crossing the language boundary and training a parser on one language and applying it to another language. Obviously, the main goal is to be able to do something for languages for which you don't have any resources, any data set at all. But also, obviously, I hope we want to do it or test the approach with languages where we actually have some data, because we want to be able to evaluate how well the approach actually works. So we use these two. Then, for various technical reasons and context of the project in which we did it, we actually did not use dependency parsers, even though these tree banks were dependency tree banks. Instead, we experimented with two constituency parsers, which meant that we had to convert the data we had from dependencies to constituents, which is doable. I don't have time to discuss all details here. Typically, it means that you lose some information in the process, but the core syntactic structure is still there. And we use two parsers, the so-called Charniak parser, named by Eugene Charniak, who was the main author of that. And then the second parser, I call it just Brown parser, but Brown University is the place where Eugene Charniak was affiliated with. And the core of that is again the same Charniak parser, but this time run in a different mode. It, instead of outputting just the best parse tree for each sentence, it's asked to produce n best possible parses. So n could be something like 100 or 300 different parses. And then there's another tool in the pipeline created by Charniak's colleague Mark Johnson called re-ranker. So essentially, this is another model that is trained on various outputs of the parser, and it collects features of the parse trees, and it also has access to the gold standard trees, and it's able to re-rank this set of 300 best trees, which were originally ordered by the Charniak parser according to its own model. Using the additional features, it's now possible to re-rank them and sometimes say, okay, but according to my richer features, the 10th best parser seems to be actually the absolute best from this new perspective. And it has been shown on English that this combination pushes the accuracy even a bit farther up in comparison to the original Charniak parser. So I used these two, and then there were other resources that we could use. There was also a parallel corpus. This was because we tried several approaches to the model transfer across languages. So it was actually not needed directly for what I call delexicalized parsing. So I'm just listing it here for completeness, but we didn't need it. And then we also had a tagger originally created by Jan Hajic for Czech, but it was retrained for a Swedish text set, so-called Parol text set, that we also were able to use for the data that we had. So now let's look briefly at the data. This was way before anything like Hamlet or UD was created. So as I said, each of the tree banks had their own annotation guidelines, annotation style, and so different set of labels, and also different rules for what should be the head and what should be the dependent. So to give you a few examples, determiner in Danish was the head governing adjective, and then there could be a chain, and the adjective could govern a noun, which is quite the opposite of what most other dependency tree bank would do. So Swedish had actually a noun governing both the determiner and the adjective. So you see that if you train a model on Danish and apply it to Swedish without doing anything about this discrepancy, then the evaluation will be quite bad. Another example, numerals in Danish govern the counted nouns, while in Swedish, the noun is treated as being modified by the number. GEN here means genitive modifier, so it's typically a nominal, but with some kind of genitive marking, like Russia's way, Rusland's way in Danish. Again, the genitive governs the nominative, so the main the possessed noun, while in Swedish the nominative is the head and the genitive is the modifier, and so on. So these first three bullets more or less reflect the same design decision. And then there's another design decision that you have to take is what you do with coordination in dependency tree banks. So in Danish, the last member, if there's like 3 or more conjuncts, the last conjunct will depend on the conjunction and everything else on the first member. while in Swedish it was essentially a chain, so each conjuncture would depend directly on the previous one. So we had to do something about this divergence, so we transformed the Danish trees to the Swedish tree style using some heuristics. It probably was not perfect, but essentially looking at rules like or the comparisons like in the previous slide, we created rules for them to map the Danish style on what the Swedes would do in that case. And while you in normal setting, you could complain that now we actually have looked at the test data and we are trying to modify our data set directly to map to reflect that. Again, I should remind you that this is actually not cheating in this setting, because the real world scenario would be that we don't have anything for Swedish, and we are happy if we get anything that looks like a reasonable syntactic structure according to some theory. So if we only have Danish following some theory that the Danish authors thought would be a good theory for their syntax, then we will be happy to have the same thing for Swedish as well. And at this from the same angle, we could also say that the Swedish theory, the one that's in the data that we should not have, is actually the good one. So then the second thing that we had to do, as I said already, we had to convert dependencies to constituents. Yes?
So in the first bullet point, you harmonized the Danish tree bank to the Swedish tree bank, or?
Yes.
Okay.
I could do the opposite as well. I just need them to follow one annotation style. I could also, if universal dependencies existed that time or something other that I would believe is a good common annotation style for everything, I could convert both of them.
Okay.
So that was the first bullet was in the dependency world, but then we converted dependencies to constituents so that we could use them with the two constituency parsers that we had. There are multiple things that you can do when converting dependencies to constituents. So I'm just noting here that we always created the flattest possible structure when creating the non-terminal. So essentially, you take a head and all its dependents or its direct dependents, and you say this is a phrase.
Sorry, another question.
Yes.
You said that the transformation is not perfect. Isn't that problematic? The fact that the translation is not perfect from the Danish tree bank to the Swedish tree bank.
You mean the harmonization?
Yeah, the harmonization.
Well, it will never be perfect. It's I mean, frankly, I don't remember whether and to what extent we neglected some of the rules that we were aware of. But even if we try to really follow everything what we have seen, it was still just based on observation. So I looked at a sample of the trees and found out how they did it. I did not have a thorough and large comparison of all their rules, so it's quite possible that I missed something. And yes, that would be a problem. But remember, all this uh, all these techniques are essentially just heuristics, just approximation. So it's quite likely that there would be much larger problems than this.
Okay.
So we then converted the morphological tags that we had for both. Each of them used completely different tag set as well, but we converted both of them to the Pentry Bank tags of English, so that the Charnik parser would be happy with that. That's because the parser actually, it could work with other text set than the this English one, but that would mean some non-trivial tweaking. So the easiest thing to do was to just make it believe that it works with English. Then when converting to constituents, you have to invent the non-terminal labels because they don't exist in dependency trees. So, but non-terminal label typically is like NP for noun phrase and VP for verb phrase. So we essentially, in most cases, we just took the part of speech tag of the head, and if the head was a noun, then we said it's a noun phrase. If the head was a verb, it was a verb phrase. And sometimes it could happen that there is an adjective phrase or something, because those happen as well. But again, it's approximation. All this, as I said, with the goal to make the parser believe it works actually with the Pen-tree bank. And now here are some numbers. So first of all, to see where we actually are without this cross-lingual transfer, we just trained the parser on Danish and applied it to Danish, and we did it lexicalized. So for this experiment, the parser still was allowed to look at the actual words, and so that we know what the not baseline is, because this number is actually higher than we would expect for the other things, but what was the performance of the parser on this kind of data. So we got 78%. This is not accuracy, it's because it's for constituency trees. You have to compute precision and recall of the phrases and then f-score of them. So this is f-score, 78% for Charniak, and you can see that the Brown parser slightly increases the score, but probably it's not statistically significant improvement. We didn't do the statistical tests for this. And again, to give you the context, the training data that was available for Danish was almost 100,000 words, while the test was 5,000 words. For Swedish, we have more than twice as much training words, but the test set was of similar size. But since you have larger training data, you could expect better model with better accuracy, and it's actually not the case. But again, that's not saying that Swedish is more difficult than Danish. It could be due to multiple factors, like more difficult domain in this data set than in the Danish one, and so on. So but roughly it's very similar. 70, almost 78 with Charniak, and a slightly more visible improvement with the Brown re-ranker here. Now, we also tried still with the lexicalized parser to simply take the Danish model and apply it to Swedish without any tweaking with the tags. And as you can see, the accuracy dropped dramatically. This would not be the case these days with modern parsers. It has been shown since then several times that the newer parsers typically are quite happy with using a different language if it is only slightly different, and with all these word embeddings and other stuff, they can work much better than this. But in these old days, really showing the parser the wrong words mattered a lot, because the parser was used to look at the word forms, and when it didn't see them, then the accuracy or the f-score dropped to 43, and Brown was even worse. Now, finally, these are the delexicalized examples, but still, in this case, in this line, we stick within one language. So in this case, we train on Danish and apply it to Danish. But the purpose of this experiment is to see how much we lose if we remove the words and only look at the part of speech tags. And while I would normally expect that the accuracy will drop, because you now have some information lost from the original data, it wasn't the case here. I don't have an explanation for that. We would have to do some thorough analysis, but it's slightly better without the words. So if you just look at the text, you have now 79, and with Brown even over 80, while what we compare it to is the first line there. And the delexicalization actually is not just using the part of speech text from the Pen-tree bank, which are very coarse-grained, but we also did one other thing. We used the Pen-tree bank text set for just the tags, where the parser expected to see the tags, but where the parser expected to see the words, we also supplied something, and those were different tags which were more fine-grained. There were more features encoded about morphology, like singular, plural, and different types of pronouns and so on. And this was the HH-like text set from the tagger. So we pretended that these were the actual words. So there was a bit more information for the parser, but
I,
still
I don't
less information than the word forms would be.
I don't understand. You put, instead of the words, you put tag set tags.
Yes. So you could do two things. You could either simply remove the words and only leave the part of speech text here, and the parser still assumes it wants to see some words somewhere, so you would have probably to put underscores there or dashes or whatever. But instead we took another text set with more fine-grained tags, but still it's a set that that can be made common for both the languages, and we put it to the word field. Is that
What
clear?
was the rationale behind that?
To provide some more information, because these tags were available for the two languages. So the
Yeah,
whole
but
idea is that normally when you are trying to work with a new language, getting a tagger for that language might be easier than getting a parser, because a parser needs a tree bank, and a tree bank is very difficult to obtain.
okay.
So we wanted to give the parser as much as we can without giving it a tree bank. Now for Swedish, the same experiment trained on Swedish applied to Swedish, but this time it actually does what you would expect, that it's slightly worse. So instead of 7781, we now have 76.07 for Charniak, and slightly better for Brown. So, and finally, this is the actual experiment trained on Danish and applied to Swedish. And not surprisingly, it's getting down, but not as much down as with the naive lexicalized approach. So now really using the tags helps keep the accuracy above 50%. It's obviously it's questionable whether 65 or 66% of F-score in syntax gives you data set that you can work with in downstream understanding applications or not. But this was the pilot project, so getting something over 60 did not seem to be useless. It seemed to be sort of uh, promising, at least. Now, one other possibility of how to look at the actual evaluation is to take the Swedish data and look at the learning curve. So if you train the parser on Swedish instead of Danish, how many Swedish manually annotated sentences you need in order to achieve the same accuracy as with the Danish model? So in other words, this tells you how much your technique, how much labor it saved you. Because if it saves you just I don't know, 5 annotated sentences, then it's probably something that you could obtain easily. But here on the graph, it looks like the accuracy we got could be achieved by approximately 1500 Swedish sentences, and that already was not so easy. That means that you would need annotators that would work for many weeks to achieve that. So that seemed somewhat reasonable, even if 66% is still not as good as we would want to see it. So that was the initial experiment with that. Then later on, this topic was picked up by Ryan McDonald and colleagues from Google, and they finally applied it to dependency data sets directly with dependency parsers. And it was this seminal paper from EMNLP 2011, multi-source transfer of delexicalized dependency parsers. What they used was a transition-based parser, so something like Molt parser, for instance. pseudo-projective technique to use with non-projective dependencies. If you don't know what that is, it doesn't matter. It's not so important now. And since they needed part of speech tags, so what they used was the Google Universal Part of Speech Tags. And they tried two scenarios. First, they tried the gold standard tags, and second, they tried tags projected across a parallel corpus from English. So in this case, this was more realistic because that's what you would have if you really tried to use it for a new language. If you don't have a tagger for that language either, then the only thing you can do is to try to project the tags first, and then you can project or cross transfer the parsing model. They only evaluated sorry, the unlabeled attachment score, meaning you look at the structure, you want to see the correct word identified as your head, but you you ignore the label of the actual relation between the head and the dependent. And unlike the experiment that we did with Danish and Swedish, they did not try to harmonize the tree structure. So that actually means that they observed that Danish was the worst possible source language for Swedish, which normally should not be the case. But because Danish happened to be the Danish tree bank, the particular annotation style happened to be so different from many other tree banks, you could do much better with other languages if your target language was Swedish. This is a copy of their results table. So this is a source language, source training language, and down here you have the various target languages. So obviously the diagonal should have the highest numbers everywhere because you are training on the same language on which you are testing it. So Danish to Danish is 79%, while Danish to Swedish is 44.5%. And if we want to see what should then be the best source language for Swedish, then you look for the underlined number here, and it's Portuguese, 66.8. So obviously Portuguese is not so much similar to Swedish, but because of the non-harmonized annotation styles, probably the annotation styles were reasonably close to each other. So this table also shows the need for something like universal dependencies, where the annotation style could be the same for all the languages. Now I have another set of experiments to show you how this changed when finally harmonized data became available for a larger set of languages. So I did this in 2015. At that time, universal dependencies already existed in its first version. I did it on our project data called Hamlet 3.0, but essentially it was more or less the same as the style of version 1 of universal dependencies. So you could view it as doing it on the first version of UD. And again, we looked at unlabeled attachment score, and we only trained on the first 1,000 sentences of each language, so that if you look at at what language helped where, it's not biased by some languages having much larger training set than other languages. And for each target language, the model was always trained only on one source language, not on multiple languages. So here is the compressed results graph. I don't expect you to get in detail each of those scores, but there is always four differently colored bars for each target language. So the flags and the groups here are by target languages. And the first one, the blue one for each language, is the lexicalized in language training. So you don't transfer anything from other languages. You just so here what it is, Hindi. You train uh, a model on the first 1,000 sentences of the Hindi tree bank and then applies to the Hindi test set. The second one, the orange bar, is still just train on Hindi, apply to Hindi, but this time delexicalized. So the words are lost. So as you can see, in most languages it drops, but not the same amount everywhere. Sometimes it drops only a tiny fraction, while for Hindi it was more visible. And then yellow and green are delexicalized transfers from other languages. And it's not always the same language. So the yellow one is the best possible source language that's different from the target language, and the green one is the second best possible source language. So remember, this is like if we had an oracle which would always tell us what is the best possible source language. We don't know that actually, but because I tried it for all possible source languages, I could select them afterwards. But this is still an important question that will have to be solved. If you apply to a new language which you don't know anything about, then you will have to know uh, how possibly you could select the source. And you can see that there are some remarkable differences, like Latin and Gothic is very difficult uh, globally. So even if you have Latin data, you still don't get very nice accuracy. Is just slightly over 50%. Uh, Gothic is a bit better, but most of the languages go over the 70s or even some of them over the 80s. And for some of them, there is a huge drop when you use the delexicalized transfer. So, for instance, this is Dutch, and there didn't seem to be any useful source language for Dutch, while for other languages, especially the Romance ones, where they are here, it wasn't that bad. So this is the global picture. Now, it was also for the first time possible to look at the set of languages and see what is the best possible source language for each language. Again, this is like if you had an oracle, or if you tried everything and then were able to analyze the results. So that's exactly what I did. And now finally you could see the groups of languages that you know are genetically related. So they typically also were grouped by the accuracies of the transferred model. So for Czech, the best possible source language was Croatian, and the second best was Slovenian. And for Slovak, again, these two, you could ask yourself why they are grouped together. I don't have an answer for that, but obviously there would be something about uh, the structure of the annotation being somewhat more compatible with everything else than for other languages, because as you can see, Croatian is the best possible source language for all the Slavic languages. It's a except itself, because it was not allowed there. So then Slovenian was the second best one. So that's a question that's difficult to answer, why some of the languages are better than others. But still, even if we have harmonized data like UD, they were converted from something else, and there probably still can be traced uh, some biases towards the original annotation, which could also be one factor that will explain that some pairs are more similar to each other. One outlier here is Finnish. For some reason, it became the second uh, best helper for Slovenian, but the first one is still Croatian. For the Romance languages, again, mostly the picture is like the Romance languages stick together. Uh, Surprisingly, sometimes it's very close to the original, or even I don't see the example here. I don't remember why I highlighted French. because it is still not better than Spanish, than training directly on Spanish, but it's very close. I think there were even examples where using a foreign language gave better results than using the native language, but it's not here. And then Romanian is an outlier even geographically in the Romance languages. So I'm not completely surprised that the Romance languages didn't help with Romanian here. For Germanic languages, it's a bit farther apart, and some of them, like German and Dutch, uh, completely fall out of the group. But at least for Swedish, we now see that Danish is a good source, and for Danish, Swedish is a good source. So at least this old observation of MacDonald and others is now dismissed. But nevertheless, when we try to recreate the learning curve, so the picture that I showed you some slides ago, for the new parser, it is much less optimistic because the shape of the learning curve for the mult parser was different from the old Charniac parser. So also the number is not directly comparable, even though we have 66 something here and we also had 66 something in the initial experiment. Remember that the initial experiment was with converted constituency based trees, so it was F score and it was not direct dependency accuracy. But the more important thing is that uh, this point on the curve corresponds to only 75 sentences of Swedish training data, which still is not something you get completely for free, but it's probably much easier to obtain than 1500 sentences. So the Delexicalized approach became less and less useful because you then pay them for getting like 100 annotated sentences, and you are likely to get something similarly good as with a delexicalized transfer, depending on the language. But arguably, for some languages, the native speakers may just not be available, so delexicalized parsing will still uh, be at least somewhat helpful. So now final part of my talk, how we actually select the source language. Because as I said, so far it was like having an oracle or trying all the languages or whatever. So one thing that you could do is using multiple source languages. You could train on multiple languages. Why not? If you can convert all of them to a delexicalized standard, then you will at least have as much training data as possible, and hopefully also somewhat neutralize the impact of some style from the others. So that's the first alternative here. You just concatenate all the tree banks and use it as one huge training corpus. Then a subtype of this could be, maybe you want to use some weights. So for one tree bank, you may take only one part of it, or for another tree bank, you may take multiple copies of it, so that they affect the training data differently to a different degree. So, for instance, if you believe that French will be a better source language for Spanish than Irish will be, but you still want to see what happens if you add Irish, then maybe you will add one portion of Irish and two portions of French, for instance. Then the other alternative would be train on each source language separately. So you have multiple models and multiple parsers, and then you can use those parsers to vote about the final outcome. Uh, so you could vote about each node's incoming edge, each node's parent, and then you could again have weighted voting. So if you believe that one of the parsers is more likely to give you the correct answer, then you could give it a higher weight. Again, there's a question how exactly you should create the weights. And then the other problem with this is that the result should be a tree. So instead of voting about every node separately, where obviously that could lead to a cycle, you could instead use the Chuliu-Edmonds algorithm, which is part of the MST parser, for instance, which in a complete graph will find out if you have weights for each of the edges in the graph. It will find for you the best weighted subgraph, which is a tree, which doesn't have cycles in it. So that's the other possibility what to do. So then the question is how to assess the weights, or how to select the best possible source if you use just a single source language. How to find out that a tree bank will be a good source for another language. So obviously what we cannot do is we cannot compare the trees, because even if we have them for our toy experiments, when we are evaluating this, we will not have trees for the target language when we want to apply this in a real world scenario. So we have to use something else. One thing would be to look at the linguistic studies about language genealogy. That's what I kept repeating here. Like, if it's a Slavic language, use a Slavic source. That's what you would hope would be useful. The typical problem with this is that you may not have any relative language available, annotated data. So one example was in a recent shared task was that there was a Buryat data set for testing. Buryat is a Mongolic language, and there was no other Mongolic language available in the training data. So you still don't know what should you use. This is the shared task actually. So low resource languages which had either no training data or very little, very small sample of training data was this set of languages. Larger part of them was Indo-European, but even within the Indo-European group, there are significant differences. So for instance, Kurmanji is an Iranian language, which probably will be quite different from Naija and from Faroese and so on. And then there was Kazakh, Buryat, and Thai. And if you looked at the high resource languages which were available for training, then there was one Celtic language, Irish, which you might want to use for Breton, which is also a Celtic language. There were 8 Germanic languages. There were 10 Slavic languages, which you could use for Upper Sorbian. 1 Iranian, there was Persian. So that would be the only thing you could use for Kurmanji if you believe you should use something closely related. There were 2 Turkic languages, which might help with Kazakh. There was nothing related to Buryat and Thai. So this is a problem that often happens. So then the second problem is that even if you have a related language, genealogically related language, it does not necessarily mean that the characteristics that are important for parsing will be similar in the 2 languages. And here's an example. Germanic languages. English is Germanic language. It's isolating. There is a rigid word order, which is the main device to tell you what is subject, what is object, what belongs where. German uses morphology. The word order there is significantly freer than in English, even though it is still bound by various rules and rather peculiar ones, with verbs being at the end of the sentence, or the subordinate sentence and so on. And Icelandic is also a Germanic language, and it has preserved even more morphology than German. So this may not be what you want if you just say, okay, these languages are Germanic, I will put them together. So you may want to look at the Walls features. Again, the thing that we did the first week, even though, as we said, Walls features are not perfect, some of them are missing, so you have to be careful about that. But at least if you look at it as a human, not just automatically select everything, then you may be able to find out what would be more promising. There's another possibility that people have tried: use language recognition tool. And if you tell the recognizer, if you give it only the set of languages that uh, you have parsing training data for, and then you ask the recognizer to recognize for you the target language, it might point at one of the most related languages. The problem is that language recognition tools typically rely too much on the orthography, and the orthography may be very different even if the syntax is not. So here are some examples. In Czech generál přeskupil síly ve Varšavě, in Polish generál přegrupoval síly v Varšavě. You can see that even though it's very similar when I read it, it is still quite different in the orthography. Russian is still similar, sort of, to Polish, but it's a different script. So these approaches did not really work, at least not as much as the people hoped for. And finally, you can try to measure tree bank similarity based on what you see in the either raw data or data that is annotated but at a level below the syntactic parse trees. So once again, uh, if we have part of speech tags, we may want to look at the part of speech tags, and that will tell us something. So now I'm getting to work there that Rudolf would actually be the better person to report on, because it's mostly his work. Essentially, you can look at various n-grams, like trigrams in this case, of part of speech tags in the corpora that you have, and that might tell you something about the distribution and contextual distribution of various uh, word categories in the languages. And if the distribution of the trigrams is similar, then it might be an indication that the languages are related also syntactically. So here are a few examples, like determiner, adjective, and noun is a trigram that will be relatively common in English, and it will be relatively common in German, while it is not so common in Italian, because in Italian they often have the adjective after the noun. So that's the second example here, where Italian is the winner. And none of them is frequent in Czech, because Czech does not have articles. So determiners in Czech are very infrequent. They essentially are limited to things like demonstrative pronouns. And so you could have instead a sentence boundary, an adjective and noun, and that's something that will be more common in Czech, while it will be very rare in the other languages where a determiner would be expected. So then if you have counts of those trigrams, you have too many counts, so you have to do something with them. And one possibility of what to do is the thing called Kullback-Leibler divergence. Essentially, it means you have trigrams of text, means like the 3 subsequent tags in the data set, where they are from the set of universal part of speech tags plus the special tag for sentence boundary. And you can get a probability distribution of the trigrams in the corpus, which means that for each trigram X, Y, Z, you will get the count of that trigram and divide it by the size of the corpus, so by all the trigrams that you have observed. And you need to do some smoothing so that non-zero probabilities don't exist. And then you can compute the divergence of 2 probability distributions, like distributions computed on 2 different corpora, A and B, by summing these probabilities and this logarithm, and that's the Kullback-Leibler divergence of 2 probability distributions. So you can do this for the part of speech trigrams. between the target and the source language, and that will tell you how far the target language is from the source language. And if you compute it for each source language with this particle target language, that will give you some hint about which source language seems to be the most promising one. And I will not go into the other details. Again, there is the citation of the paper as with all the previous ones. And at the very end, I want to mention one more paper by Laurien Offram and others, which tried to assess a similar thing, actually, that sometimes the word order of different part of speech categories is different in the two languages. So if you happen to select a source language that differs in some aspects from your target language, like again English and French, it would be like English and Italian in the table I had 2 slides ago. In French, it's more likely that, or at least more likely than in English, that the adjective will be after the noun. So la question suivante, suivante corresponds to following in English. You may want to do some reordering in with the source language so that it's more similar to the target language. And then the parser, especially if it's a transition-based parser, which relies on local context, so it relies on word order quite a lot, then it will see not only the part of speech text and the relations between them, but it will also encounter the part of speech text in the ordering in which it is likely to find them in the target language. So then again, there were some heuristics about how exactly to do it, especially how to find out what the word order uh, uh, properties would be. And again, one of the possibilities that they tried was they used heuristics based on the word atlas of language structures, but also they tried a language model based on the part of speech text, so something that we used for the Kullback-Leibler divergence. And then again, as with all the papers that I refer here on, you would have to actually read it if you wanted to really implement it, because there's a number of other tweaks that they did. But I'm already over the time that I had, so I should stop now. Questions? If not,
So,
then I think yes, Chris.
so the success rate of the parser doesn't only depend on like the closeness of the two languages or the closeness of their respective tree banks. It depends on how it is built itself, right? Because you just said that it depends on whether the parser, for example, looks at these kinds of features or something like that.
I don't remember whether the parser, the last one that I mentioned, actually had a detailed analysis of different parsers. They said that for a transition-based parser, this will be very important and very devastating if the word order is different, which I agree with, but I don't remember whether they also showed that for a graph-based parser it's not so important.
So it depends on like these three things, right?
Yeah, that I think that's always true. Various parsers will make various types of errors. So uh, yes, in this case, they obviously try to address one particular set of errors that may not be so severe in the other parsing strategies.
Okay.
But obviously there are other important things like the size of the training data. That's very important.
Yes.
Yeah.
Okay, so I think Rudolf, it's your turn now.
Okay, thanks. I'll try to share my screen. Fine. So hello everyone. So as usual, Dan talked about delexicalized parsing and delexicalized parser transfer, and this is exactly what we'll try to do today in the practicals. Today's practicals will be pretty straightforward, I would say, and also the homework assignment will be pretty straightforward. So it should be kind of a chance to relax with doing something quite simple. So let's see. So the idea obviously is to try the Delexicalized parser transfer. And for that, I have trained and prepared some Delexicalized models for UDPipe. So they're here for download for some of the languages. And then there are three language groups for which we can try to do the experiments where it makes a lot of sense to transfer the parsers between the languages. So this is what we'll try to look here at. What we need to do to be able to do the task, especially the evaluation, is to actually download some test data. So obviously, in real world where you would want to use Delexicalized parsing, so it's in the case where you don't have the tree bank for the language which you want to parse. So you actually cannot really evaluate the accuracy appropriately. But as usual, we will simulate it by using tree banks for languages which we have. We just won't use it for training, only for testing. So unless you already have some universal tree banks downloaded, it's a good idea now to start downloading, because it's some, 300 megabytes or something. So if you have the option to download it, it's a good idea to do it, because then you can work on the assignment immediately. So I will just copy the link to the UD Trimbanks collection. We have the new 2.5 one already. And I hope you now see the terminal. So I will just download the collection. And yeah, it's quite fast, but it may be slow for you. And it's TARC zip format, so you have to unzip it with some tar magic, which I always forget, so I have written it down. So tar minus ZXVF.
Why did you just speed shame us, Rudolf?
Sorry?
Why did you just speed shame us? Internet speed shame us.
I don't understand what you're saying.
That might be slow for us.
Okay. I'm still not sure what you're saying.
Nothing. It was just a joke.
Okay. Sorry, I didn't get it. Never mind. You can explain me later. Okay. Fine. So once you download it, you need to unpack it. And why doesn't it? Okay. Just think I got this file. Yeah. So when I unpack it, I should get the tree banks for all the languages in UD 2.5. So this is something we'll need to actually evaluate the models. Okay, it will take some time unpacking. Fine. So so we need to test it on something. So that's what we'll try to do. And this is what I'll show now. And then in your homework assignment, you should train the Delexicalized parsers for other languages. And fortunately, we've done something well, maybe you've done it already or you're working on it. The previous homework assignment was to actually transfer part-of-speech tags from one language to another, which means now for the target language, you already have data with some part-of-speech tags, which is a good input then for the Delexicalized parser. Okay, so I hope I have it unpacked. Yes. So this was the command that I used for unpacking. And let's try, for example, the Czech and Slovak transfer. Okay, so I will download Czech and Slovak parser models. Okay, I don't think this way. And I can also show, okay, these are the two commands that I use now. Okay, I want to download the Czech Delexicalized parser and also the Slovak Delexicalized parser. And now, and I need the UDpipe UDpipe tool, which I already have here from the previous task. So now I should be able to test the lexicalized transfer approach on Czech and Slovak. So let's see what happens. So to run UDpipe, we now will run just the parsing because the data already contains tags, and in the lexicalized parsing, you need the data to already contain part of speech tags. So we will just parse the data. And if we are not interested in the output and we just want to measure the accuracy, so you can pass the command -- accuracy, and it will not output the data, but it will just measure the accuracy on the test data if the test data is annotated. So let's first look what we have here, right? So I will need some Slovak tree bank, and okay, how is that? Okay, no, Slovak. Okay, there is one Slovak tree bank, and I will need the test part of data in the CONLU format. So there is some data, and we will use the delexicalized parser, so it will only look at the part of speech tags. And now again, we're making it quite simple. So data are already harmonized. They already use the universal dependencies part of speech tags. So this should be easy to do. And so let's just, I don't know, see that there is something. And I have these two models. So the Czech and Slovak delexicalized model. I will also, okay, let me also download the lexicalized model. I always also have Slovak lexicalized model and Czech lexicalized model. So these are the other two, the one with supervised. Okay, and now let's run UDpipe. Let's see what happens. Okay, so the upper bound should be if I use the standard. Okay, I want to parse it. I want the accuracy, and if I just use the standard model, so this will be Slovak supervised parser. So this one, it's trained on Slovak data. We are testing it on Slovak data, and it uses part of speech, but it also uses word forms. So this should be kind of the best we can get usually, if we have enough data for the language. So, and we can see we are getting some 86% unlabeled attachment score and 84% labeled attachment score. So that's pretty good. It's not perfect. And let's try what we lose just by using the delexicalized parser. Okay, so now I'm running the same thing. So I will parse the Slovak data using still a Slovak parser. So this is still what we're in the end not interested in, because we're interested in situations where we don't have the training data, so we cannot train a parser for the language. But just let's see how much we lose by removing the lexical features. So it doesn't look at words, it just looks at their part of speech. And yeah, we can see that actually we don't lose much. So we've lost 1 percentage point. That's pretty good. So it seems that the word forms, they, at least in this case, they only add a bit of information. And for different languages, you will get different results, as Dan showed. Sometimes even the delexicalized could be better than the lexicalized. Okay, so that was fun. So now let's try to do the cross-lingual transfer, which simply means changing 2 letters in the command that I'm running. So now we know how the Slovak model works on Slovak data, and we can assume that the Czech parser should work pretty well because Czech and Slovak are quite close languages. So I will run the Czech delexicalized parser on the Slovak data.
So the delexicalized parser does exactly the same thing as the lexicalized, but instead it doesn't look at the word form. That's just the
Yes.
only difference. Right?
Yes, exactly. Yes, yes, yes. It's trained basically in the same way. There is the example training command on the web page, and just the setting for the parser to be delexicalized is that you say that the form embedding has 0 dimension, which means, yeah, for the word forms there are no embeddings, so it doesn't look at word forms. That's the only difference, really. Okay, so now we've got some results for using the Czech parser on the Slovak data, and we can see that the unlabeled attachment score is 71%. So we're something like 14% below the Slovak parser, but it's still reasonable. 70% is pretty good. As you saw, then a reasonable way to evaluate how good this is would be to train a Slovak parser on, I don't know, 100 Slovak sentences annotated and see whether this corresponds to annotating 100 sentences or 1000 sentences or how much. So that's actually something you can do as part of the homework assignment if you use a language which does have training data. So to estimate how good the cross-lingual methods are, how much annotation work they could save. So there is still some gap, of course, because there are some differences in the languages, there are some differences in the data, there might be even some differences in the annotation. It's harmonized, but it's not always 100% harmonized. So some things might be annotated differently in the languages, but it's pretty good. Since we also have the lexicalized parser, so we can even try to use the lexicalized parser. Now, this only makes sense if the languages are quite close, because now the parser was trained on Czech texts, so it was trained on Czech word forms, and now we will apply it to Slovak text, to Slovak word forms, which are similar to some extent. Some words are exactly the same, but a lot of the words are different. So it makes sense to some extent. So if the languages are quite similar, then this might work. If the languages are very different in terms of the words they use, so this won't work at all because it will just be all unknown words to the parser. So let's just see what happens. And the supervised parser is, the model is larger, so it takes more time to parse it. And you can say that, hey, so for Slovak, it's so close to Czech that you even don't have to delexicalize the parser. So the lexicalized parser will obviously be confused in many cases because it won't know some of the words, but a lot of the words are exactly the same. A lot of the function words are actually exactly the same. So it will probably help a lot with, I don't know, detecting some different types of prepositions and conjunctions and such stuff. So in this case, the lexicalized parser is even better than the lexicalized parser of it. But it's really only, yeah, yes?
Yeah, can I ask a question? Yeah, like if one letter differs between two same words between the languages, it's over for the
Yes.
like.
Yes. Of course, it depends on which parser you use. So with this version of UDPipe, it does compute some word embeddings of the words, but these are for the whole words. So the whole word has to match exactly so that the parser can work with it. And even so, like these languages are so close that it does happen. You could use a different parser, which maybe is able to look just at parts of words, or if you used maybe fast text word embedding, so they are computed for subwords, kind of. So then it could handle even words that are just similar. In this version of UDPipe, it cannot. It just has a dictionary of the words it knows, and any other word is unknown. But still, okay, so these languages are really super close.
Okay.
We can try the same on some other languages. So we have Norwegian, Danish, and Swedish. We have Spanish and Portuguese. So I suggest that you now try to do the exercise as well yourself. I will probably try the Spanish and Portuguese now as well. And just if you have the option, so if you have downloaded the models, then well, the models are easy to download. If you have downloaded the tree banks, this is the large data. The models are kind of small, so try to do it to see whether it works for you. So I will be doing it now for Spanish and Portuguese, but feel free to even try the Norwegian, Danish, and Swedish, which is kind of the original languages on which Dan and his colleagues tried to do these experiments originally. I will try Spanish and Portuguese.
I think Martin asked a question in the chat group.
Yeah, I have it. I lost the chat window somehow. How do I open it? Yeah, here it is. How big is the dictionary in UDPipe? Yeah, good question. Well, technically, I would have to check the documentation of UDPipe, of course, but I think the default parameters are that it takes the training data of the tree bank, and it only remembers words that appear at least 5 times in the training data, I think. It's the usual way of doing word embeddings. This is definitely an option that you can choose. Maybe it tries to remember all the words in the training data. I'm not sure about that. But the default is that, well, it doesn't come with any pre-existing dictionary. So it just uses whatever words appear in the training data of the tree bank. So this means that if your training data is very small, then the dictionary will actually be also very small, and probably the lexicalization won't help the parser much. Then in UDPipe, actually, there is the option to provide a bigger dictionary, or well, whatever dictionary you want, because internally it uses word embeddings. So it just translates each word form into a vector of, well, 100 numbers or whatever you like. You can prepare such a dictionary beforehand and provide it to UDPipe on training. I should be able to find this quite quickly, I think. Dependency parsing, output formats. No, I need training UDPipe models, components, blah, 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 tokenizer, Tanger parser. Oh yeah. So it by default it computes embeddings for all these features. So for part of speech tags and for morphological features. So we can switch this on and off. And for the word form, it's a dimension of 50. And yeah, pre-training word embeddings. Okay, so if you want to, if you have some larger text data and you just need a plain text data to train word embeddings, and you can download the Word2Vec tool or the fast text tool, or well, anything else that produces word vectors. And there is the default options where how to train the word embeddings. So these are just some hyperparameters for Word2Vec, and these are pretty standard actually. And blah blah blah. Somewhere you can say that the pre-trained embeddings are in a specific file, and it just loads the embeddings from the file. I cannot now see the option, but it's somewhere there. Yeah, embedding form file, that's what I was looking for. So you can say that the embeddings for the word forms shouldn't be computed from the training data, but that you already have pre-computed them on some larger text data. And if you have some bilingual word embeddings, that's something we will cover towards the end of the course. So you train some word embeddings for one language and then you project them to another language. So this would be actually a good way to transferring the parsers between languages. I don't know if I can prepare this for next time. Well, I'll see. So then you can enlarge the vocabulary and you can have better coverage, or you can make the vocabulary smaller if you like. And this way it will be probably more transferable. Okay, I said I wanted to try the Spanish and Portuguese, so I'll just quickly try the Spanish and Portuguese as well. And let's see. So you're free to try any languages you like. Spanish, Portuguese, Delexicalized, and Lexicalized, and Spanish Lexicalized. And let's transfer from Spanish to Portuguese. I think the Spanish tree bank is larger. So I want to test on Portuguese, and there's actually 3 tree banks of Portuguese, so let's just try one of them. Okay, so there is some tree bank of Portuguese. I'll try to parse it and just measure the accuracy of let's first use the Portuguese supervised model. So if you are lucky enough and you do have the data, you should have something like 84%. If you remove the lexical features, so it drops to 83%, so a similar 1% drop that we saw before. Now, if we transfer it from Spanish, the lexicalized way, so we see 76%. So again, that's a similar, well, it's a smaller drop. It's just what 7% drop or something. And if we actually do use even the lexical features, again, that's a larger model. Now, again, for Spanish and Portuguese, it works even better with lexical features. Now, what I think actually happened is that I trained the models on some older version of UD. So definitely I didn't train it on UD 2.5. So it's possible that something important for parsing changed in the annotation for part of speech tags. And then it's good not to rely only on part of speech tags, but also on word forms. I don't know. You should definitely, in your homework assignment, you should definitely train it on the new data. Yeah, I trained it on UD 2.1, so there were some changes. And something I also wanted to say, so then it depends also on which tree bank you use, of course. So there are different kinds of tree banks, and the results might be different because just different test data look differently. So we had 76 for the delexicalized on the BOSC tree bank. We have 72 on the delexicalized on the GSD tree bank. And then there is also the parallel tree bank. It's, tree bank annotated in many languages, the same sentences. So these are simpler sentences, and here, okay, we get to 69. So it depends on the data a lot as well. So I'll still rerun the third thing to have these 3 numbers. So these 69, 72, and 76. These are all accuracies of a Spanish delexicalized parser evaluated on a Portuguese test data. And we can see that there is basically a 7 percentage point difference. So it's not only the pair of the languages, but it's also the style of the data. So if the sentences are longer, shorter, what kind of domain is it? Is it mostly news, or is it from the internet, or is it, I don't know, subtitles from movies? These have different syntactic structures, so the parser is trained on a different thing. So this is something we talked about, I don't know, last week, 2 weeks ago, that one thing is the language, but the other thing is the domain. And you can see that there is a similar drop of 7% by going from Spanish to Portuguese, but then again, you can get another 7% drop just by using a different kind of text, or maybe text annotated in a different way. So even the same, the data for the same language can behave differently if it's different data or different annotation. I can even try to see, I think I trained the Portuguese parser on the on the Bosque tree bank. So I can see if I evaluate it on the Bosque tree bank and on the parallel tree bank. So I'm taking now the supervised Portuguese parser and evaluating it on the various Portuguese tree banks. There are 3 Portuguese tree banks in the data set, and some of them might be just more difficult to parse. Okay, so you can see that it was probably trained on the Bosque data. So on the Bosque data, it has 84%. And now I'm using a Portuguese parser on the PUD data, and I'm only getting like 72%. So that's very low. And if I use the Spanish parser, I got 69%. So that's already very similar. So the difference from going to from Spanish to Portuguese, and the difference of going within Portuguese just to a different data is similar. You get a large drop in accuracy in both cases. So we're mostly focusing on the case where we transfer from one language to another, but when you just transfer from one domain to another, it's a similar problem actually. I just want to avoid on the GSD as well, but GSD should be closer to Bosque, I think. Let's see. Oh no, it's also like 71%. So it's not only the language, it's also the tree bank annotation style, tree bank data style, domain, whatever. Okay, so now to the homework assignment itself. So yeah, I didn't show this command. This is to train, this is what I used to train the Delexicalized parser. So you take some training data, you say to your pipe that you want to train a parser, and you turn off the embeddings for the word form. And also I suggest turning off the embedding for the morphological features, so that you only use the part of speech tags, because the morphological features are not super harmonized across languages. And you say that you don't want to train a tokenizer or a tagger because you already have tokenized and tag data as the input. And the input for the testing then should be actually the output of the previous homework assignment. So in your previous homework assignment, you should produce part of speech tagged data for language. So the task was to project the part of speech labels from one language to another language. So you already should have text with part of speech labels in a language projected from another language. And so you should just work on that and try to also parse such a data. So again, you should choose a source language, probably the same which you used for projecting the part of speech labels, but well, you can try a different one as well. And you should apply it to the part of speech tag data that you have. And again, if you do have test data for the language, so try to measure the scores. If you are using a language for which there are no test data, so just try to, well, look at it a bit, try to guess how well it seems to work. Well, I've shown the visualizer of the syntactic trees before, so obviously, if you're not an expert on syntax, then it's hard to say, but you can at least look, okay, are the subjects and objects identified correctly, or such things. And you can also try what I tried here. So I call it the source lexicalization. So it's where you train a standard parser, which is lexicalized. So it all looks at the word forms and does it work better or worse. Still, it's usually a good idea to turn off the morphological features. And you know that we actually didn't focus on cross-lingual projection of morphological features in the previous assignment. So we don't assume actually that you do have them. And yeah, if the vocabulary is shared between the languages, this should work. And that's it. That's the homework assignment. So no rocket science this time. So basically, you need these two commands that are listed on the page, and just use reasonable data and report what you found. So that's kind of relaxing assignment, let's say. And as Dan showed, you can also use multiple source languages, and you can have them kind of vote on the best structure. But voting on part of speech text is easy. You just choose one. Voting on tree structure is hard because you need the output to also be a tree structure. So there is some points on how you could try to do that using an implementation, which unfortunately is in Perl. So you have to push it to the Perl script and so on. So that's completely voluntary, and it's not super important to do that. So it's just only if you are really interested in the task and you want to try combining multiple source languages, but it's not super easy to use, so you don't have to do that. So it's completely sufficient just to do the basic thing. But yeah, you should just try to look at the results, try to comment on it. Ideally, you should try multiple source languages. Of course, for Portuguese, if I use the Czech parser, so it will probably work much worse because Czech and Portuguese are not very close. Let's see what the result will be. Yeah, okay, 64%. So it's not that bad, but it's definitely worse than any other numbers that we had. So that's about it. Now the deadline is usual till next week Sunday, and I hope that today I will look at the assignments that you've already submitted. I haven't yet, so sorry for that. I will be sending out some feedback. And one important thing at the end, if I'm not mistaken, then next Friday it's the state holiday because it's Easter. So we should see each other in 2 weeks' time from today. Is that right? Can somebody confirm? Nobody knows. I think so. Otherwise, that should be all for today. So if there are any more questions, feel free to ask. And otherwise, this will be all.
Okay, thank you.
Thank you. Bye.
Okay, thanks. Goodbye. Enjoy
Bye.
the weekend.
Bye.